Howdy, Jack, and welcome to your Chemistry Chapter 5 lecture. Chapter 5 is all about gases, and gases are fun to study because they're pretty easy to work with, but more importantly, they're actually, believe it or not, the second most prevalent phase of matter in the universe. The first, or the most prevalent phase of matter in the universe is plasma. And really, even before they came up with the nuanced difference between a plasma and a gas, people thought that gases were the most prevalent matter. But of course, we've since realized that plasma does exhibit different characteristics than a gas does, and so that's why plasma has been defined as a separate phase of matter in addition to gas, liquid, and solid. So, what this lecture is going to cover, this particular lecture today, is going to focus on sections 5.1, 5.2, 5.3, 5.4, and a portion of 5.6. The other sections that haven't been covered yet in this lecture, we'll get to later on in the second video. So if you've not already done so, you want to make sure that you go through and read these sections. And I would even encourage you to do so even before you watch the rest of this lecture. The way that I present the material in this lecture is not going to follow exactly the same path or the same flow of content that the textbook sections flow. Instead, I'll be synthesizing all the information for you as a collection of all of this information into this lecture. So before we do that, I do want to just very briefly take you through how to read and take notes from a textbook, particularly a science textbook, but you could probably also apply the same approach to mathematics. Okay, so this particular textbook, this chemistry textbook, I've learned that it gives a lot of details, and the details are sometimes a little bit too involved for the level at which you're learning chemistry. So you want to read the paragraphs, right? And some of them are fairly interesting. But when you really want to take notes, most especially, is when you learn something new. Okay, so reading through these top two paragraphs, for example, a gas uniformly fills any container, is easily compressed, and mixes completely with any other gas. Well, my guess is that you already knew that prior to reading that statement. So you wouldn't need to take a note on something like that because you already know it. But as you go through and you read some of these other things, and particularly in the second paragraph, they're giving you information about something that's pretty interesting. But quite frankly, it's only interesting perhaps if you've actually observed something like this before, where you fill a metal can with boiling water and then you seal it and let it cool and then it condenses, right? That's actually a fairly neat demonstration, and we could actually do that here at home if you wanted to. But again, there's really not anything to write down or take notes on, and so I myself wouldn't bother to take notes on that. Then you get into the third paragraph and you're learning about a barometer. Now, there's a possibility that you haven't learned what a barometer is. And so that would be a good thing to write down. Basically, in your notes, write down that a barometer is a device to measure atmospheric pressure. Now, these other things that are listed in terms of who the barometer was invented by Torricelli, who was a student of Galileo, those are really interesting details if you're a big fan of science, but it's not going to help you understand science any better. And so it's kind of an extraneous detail and certainly something that I wouldn't make a note of. The rest of the paragraph talks about how Torricelli anecdotally or what we would call phenomenologically discovered that the height of his barometer that he invented at sea level was always somewhere around 760 millimeters. In other words, the height of that mercury column was about 760 millimeters, right? Or to put that in English perspective, recognizing that 1 inch is about 25.4 millimeters, that's roughly 3 inches, right? So a little over 3 inches or maybe right about 3 inches would be the height of the mercury column that he observed. And so, by the way, that would be, I think, 300 millimeters. I'm having a hard time, or 30 inches, excuse me. Yeah, that would be 30 inches, not 3 inches. I missed the decimal place there. So, a mercury column of about 30 inches is roughly how much atmospheric pressure applies to a column of liquid mercury. So, things like that are interesting, but there's not really anything to write down. Now, as you start to get into more details, right, like units of pressure, what a manometer is, right, that a manometer is, again, a device to measure pressure. And then you learn things like the unit millimeter of mercury is also called a torr, right? And so those are important things. And in this statement here, where one standard atmosphere, which we simplify as writing as 1 ATM, is exactly defined as, scientifically, we define that as 760 millimeters of mercury, which because a torr is the same as an atmosphere, then, which is also the same as, because a torr is the same as a millimeter of mercury, 1 atmosphere is also equal to 760 torr, okay? And so, those would be details that you'd want to write down because it's important to remember that 1 millimeter of mercury is equal to 1 torr. And it's also important to remember that 1 atmosphere is defined as 760 millimeters of mercury, which also therefore means that it's equal to 760 torr, okay? And again, as you read through the chapter, right, there's a definition here for pressure, which is force divided by area. You may have already known that, in which case it's not important to write it down. But if you are learning that for the first time, then you want to write that down because that's an important detail. But then what's embedded in this paragraph is even more important detail, and it's when they start introducing the idea of units and how the unit for pressure is determined for the SI system. So in the SI system, the base unit for force is the Newton. That's this N that you see here. And the base unit for any length measurement is meter. And since area is a length measurement squared, the base unit in SI systems for area is meter squared. And so force divided by meter squared also has its own defined unit, which we call the Pascal. And that's what you see described in this text here, that pressure for the SI system is newtons per meter squared, which is also called the Pascal, or Pascal, okay? And so, and then they give some additional definitions. And I'm going to go over all of this here in just a little bit as we go through the lecture notes, but I'm just trying to give you a sense as to how to read through these chapters and take relevant notes, okay? All right, so let's get back into the more interesting things and talk specifically about what pressure is, okay? So I know you have a good idea as to what gases are, excuse me. So I know that you have a good idea already as to what a gas is, but what we're going to do is we're going to really provide a very specific definition for certain types of gases. And so suppose you have some kind of a volume, okay? In engineering, we typically call this a control volume. And a control volume just simply means that it's some region in space that we're interested in analyzing or studying. And why defining a control volume is important, at least from an engineering perspective, it's true in science as well. They just don't, they're not quite as rigorous about defining a control volume in science as we are in engineering. But the reason why defining a control volume is important is because it's defining for us that region of space that we really care about. And mathematically and scientifically, we only care about what happens inside that control volume and anything that the control volume does in an interaction with the environment, right? So all of this space around the control volume is what we would call the control volume's environment. And we really only care about what's inside the control volume and what happens between the control volume and the environment, whether there's a flow in or a flow out. Okay. Now you're not going to see that defined in your textbook anywhere. Again, this is more of an engineering concept because defining that control volume establishes for us how we write our equations, and which again is important as we go through more discussion here about what gases are. So we're going to assume inside this control volume that we have some kind of a gas, okay? And so I'm representing this gas basically by all of its individual particles, okay? So every single one of those little dots that you see is meant to represent a gas particle, and you can think of a gas particle as either being a single atom, for example, or a molecule of some sort, okay? And that's usually what our gases are represented as, okay? And when we say a gas particle, one of the things that we're going to talk about today is the kinetic theory of molecules, or the kinetic theory of gases. That's this portion of 5.6 that you see here. And that kinetic theory of molecules depends on the fact that these gases are composed of particles, right? They're composed of these molecules that can float around and have velocity within the control volume and have different modes of energy. We'll talk more about that here in just a little bit. But that's kind of one additional thing that I want to highlight is, even though you see these drawn as just static little dots on the board here, in fact, each one of these particles, generally speaking, is going to have some velocity. They obviously aren't all going to have the same velocity. Some are going to be going faster than others, and they're also going to all be going in different directions, right? And so remember that a velocity is a vector describing both the magnitude or the speed of that particle as well as its direction. So every single one of these particles is going to have a different velocity, whether it be a different speed, a different direction, or both of those things are different, okay? And again, this is going to become important when we talk about the kinetic theory of gases or kinetic theory of molecules here in just a little bit. But where it becomes most especially important is when we describe the idea of an ideal gas. And I'll get to that here in just a little bit. Okay, now, but for our purposes, we understand that this control volume, which is a fixed volume in space, and we're going to describe this control volume with the letter V, not to be confused with the vector V arrow, right? So just to make this very clear, if I ever draw this little arrow symbol over a variable, that arrow symbol is indicating that this is a vector, okay? So it's a quantity that has two dimensions to it, right? In the case of velocity, those two dimensions are speed or magnitude and direction, okay? If I draw the V without that arrow on top, okay, as I've drawn V here, that means that I'm referring to volume, okay? So this control volume has some amount of volume, okay? And of course, volume can have units of liters, for example. It can have units of cubic meters. If we're in the English system, which you're not learning in chemistry this semester, it could have units of cubic feet or cubic inches, right? Very similar to how the displaced volume of an engine is described in cubic inches, okay? Now, in addition to having a volume, it also has pressure. And so we use the letter P to indicate pressure, right? And this is going to have units of things like what we've already talked about, torr. It could be millimeters of mercury, right, which is, again, equivalent to a torr. It could be units of atmosphere. It could be units of what we call bar. It could be units of pounds per square inch, PSI, so on and so forth, right? And so this V is volume, and this P is pressure, okay? Okay, now we can also describe or characterize this gas with another property, which we call temperature. And of course, this is going to have units like Kelvin or degrees Celsius, degrees Fahrenheit, or Rankine, okay? So degrees Fahrenheit and Rankine, these are both English system units, and Kelvin and degrees Celsius are both metric units or SI units, okay? We'll talk more about this here in just a little bit. Just wanted to differentiate that for you right now. And so T, of course, is temperature, okay? Now, the final way that we can describe or characterize this gas in this volume is by actually providing the number of particles composing that gas in this control volume, okay? So, of course, the number of particles is what we use the mole to describe. And so we use the letter N to indicate mole, and this essentially has units of mole, okay? Mole is a really funny concept because we can't actually count the number of particles in a substance, okay? The kinetic theory of gases, allows us to know that the mole exists. It allows us to actually quantify the number of particles in a gas at standard conditions. That's Avogadro's number, for example. But it's, in practical terms, we can't describe or measure explicitly the number of moles in a system. Okay, so in a lot of ways, N, the number of moles or the number of particles composing a gas in a given control volume is an abstract concept. Okay, now in engineering, what we use is we use the non-abstract thing, the thing that we can actually measure, which is mass. And of course, mass has units of kilograms, or if we're in the British system, what we call something which we call pound mass. And then the British system also has this weird thing called slug. Okay. And again, you're not going to learn about pound mass and slug or really any of these British units like cubic feet or cubic inch or PSI, pounds per square inch, in your chemistry book. I'm just listing this for you right now so that you have knowledge of it and can kind of help create some awareness or some appreciation for it. But of course, M stands for mass. And we like to use mass in engineering because you can actually measure mass in real life as opposed to measuring moles, which can't actually be done. Okay, now real quick, before we talk a little bit more about pressure, right? Just, as a reminder, volume, I think you have a good physical sense for that, right? Volume is the dimensional volume, or it's the physical volume. That's actually a better way to say it. It's the physical volume of your gas. Okay. Oopsie, didn't want that to happen. I don't know what this is doing now. It's creating problems for me. Okay, sorry about that. Okay, so V is just the physical volume. Something's misbehaving for me here. Oh, I think I know what's happening. Okay, so V is the physical volume. I don't know why it keeps doing that, but it's really annoying me. Yeah. For some reason, it's no longer letting me. I think I must have accidentally put it. Oh, is that what I did? Yeah, okay, that's what I did. I see. Okay, I selected the wrong pen. Okay, very good. So V is the physical volume of the gas. And as already described above, that's going to be quantified in terms of things like cubic meters, cubic centimeters, or liters. Okay, now remember that the conversion between liters and cubic meters is there's 1,000 liters in a cubic meter. Okay, and then you can use the fact that there's 100 times 100 times 100 cubic centimeters in a cubic meter to then be able to translate between a liter and a cubic centimeter. Okay, and so that's sometimes a good thing to know. And then the other conversion to note is that 1 liter one liter Sorry, Jack. I'm trying to learn how to use this thing. Yeah, I don't know why it does that. Well, I'm learning how to use this. So, okay, so I'm just going to start writing down here because it seems to work for me down here. So 1 liter is equal to 1, what we call decacubic meter. Okay, so that D cubic meter is called a decacubic meter. Okay, so that's volume. We'll come back to that in just a little bit. We can also talk about temperature. And of course, temperature is typically measured in either degrees Fahrenheit. That's what we do in the English system. Or as degrees Celsius, which is what we do in the SI system. Now, both degrees Fahrenheit and degrees Celsius are what we call relative temperature measurements. And what that means is that they're relative to some arbitrary reference. Okay, so degrees Fahrenheit, for example, is relative to the normal body temperature for a human, right? That's what the Fahrenheit scale is based on, is the human body temperature. Degrees Celsius is relative to the freezing point and boiling point of water, okay? But it's still relative to something that is not in absolute terms, right? In other words, when you bring water down to 0 degrees Celsius, you can make water go colder than 0 degrees Celsius. As ice, you can go well below 0, for example. Okay, and so because you've not picked a reference that at its lowest possible value is equal to 0, it's always going to be a relative measurement. What we need, though, is we need an absolute measurement. In other words, we need a scale where when we reach 0, that is the absolute lowest we can go, okay? And so in that case, we have 2 absolute scales. In the SI system, we have what is called the Kelvin scale, okay? And the Kelvin scale basically is the temperature in degrees Celsius. So the temperature in the Kelvin scale is the temperature in degrees Celsius plus 273.15, okay? Now, what that means is that the coldest something can possibly get, the absolute lowest temperature, is 0 Kelvin, which would be the equivalent of negative 273.15 degrees Celsius, okay? Nothing can get colder than that. Even if you go into outer space, which is nearly a perfect vacuum, the coldest you'll get is something like negative 272.95 or negative 272.9 degrees Celsius. And that's because there are, in fact, some particles in outer space. Even though they're so insanely spread out, there's still some particles in outer space that causes there to be a less than absolute 0 temperature, okay? But the absolute coldest something can ever get is 0 Kelvin. Now, in the English scale, we have what is called the Rankine scale. And the Rankine scale is the temperature in Fahrenheit plus 454 degrees, okay? And we don't hardly ever use Rankine. Even in engineering, we hardly ever use Rankine. But what's important is that you understand that whenever you do a calculation with temperature, it's almost always absolutely essential that you have that temperature be in absolute temperature, okay? And I'll explain that more when we actually do some of those calculations here in just a little bit. Okay, so the next big one, of course, is pressure, right? And we've already talked about this a little bit, but we know that we, of course, use a manometer, for example, to measure pressure. And depending on what type of manometer it is, it might give us units or it might give us measurements in terms of millimeters of mercury, You could actually have a manometer that's in millimeters of water. It could be in terms of torr, right, which we already talked about as being equal to 1 millimeter of mercury. It could be in atmospheres. It could be in pascals. It could be in kilopascals. It could be in bar. Or if it's in the English system, it could be in pounds per square inch, PSI. And in some cases, some rare cases, I've seen it in pounds per square feet. You usually see that in like concrete, for example, when you're talking about how much stress a concrete can hold, they'll usually report that as pounds per square foot as opposed to the enormously large pounds per square inch. Okay. All right. So what are all of these different units? Well, first of all, atmospheric pressure, or this ATM, okay, that's basically what is referred to as an atmosphere. And essentially, it's referencing the pressure against what the atmospheric pressure is. Okay, so the atmospheric pressure, as we talked about earlier, is equal to 760 millimeters of mercury, which is the same as 760 torr. Because again, a torr and a millimeter of mercury are the same. So this is how we define the unit atmosphere. Okay, so this is atmospheric pressure, 760 millimeters of mercury, and we define the atmosphere, ATM, as being exactly 760 millimeters of mercury, or 760 torr. Okay, so that's how atmosphere as a unit, or ATM as a unit, is defined. Okay, now Pascal, where that comes from, is that comes from our fundamental physical definition of pressure, P, which is equal to force divided by area. Okay, so of course you know what a force is, right? A force is a mass that is being subjected to an acceleration. Okay, and so we use the units in the SI system of Newton to characterize force. Okay, so the letter N indicates Newton in honor of Sir Isaac Newton. And then area in the SI system is meter squared, because the base unit of length in the SI system is a meter. And so two length scales with area, right? Length times width, for example, is going to give us meter squared. And so this definition of pressure, force divided by area, with units of Newton per meter squared, is exactly how we define the unit Pascal. Okay, so PA is what we call the Pascal. And it's exactly defined as 1 Newton per meter squared. Now, Pascal is a really small unit of pressure. Okay, and so what we often do instead is we'll use a kilopascal, or a kPa, which is of course equal to 1,000 pascals. Okay? All right, so how small is a Pascal? Well, if we want to describe atmospheric pressure in terms of Pascal is 101,325 pascals, right? So that's how small a Pascal is, right? Remember that 101,325 pascals is equal to atmospheric pressure. And of course, atmospheric pressure is equal to 760 millimeters of mercury, right? So you get a sense now as to how small the Pascal as a unit is. And so that's why, for example, we'll often describe atmospheric pressure as being 101.325 kilopascals, right? We just divide by 1,000 and capture that change in 3 orders of magnitude by describing this as a kilopascal and instead of just Pascal. Okay, so I also mentioned up here in the list of units for pressure the bar, and a bar is very close to an atmosphere, but 1 bar is described as exactly 100 kPa, 100 kilopascals. Okay, so a bar is approximately equal to an atmosphere, but it's not exactly equal to an atmosphere. Okay, and then finally we've got the English units, and as you know, it's always much easier to do all of your calculations in the metric system but we tend to think very physically in terms of the English system, right? And so how do we relate this to a pound per square inch, for example? Well, what I often do is I remember that 14.7 pounds per square inch is approximately equal to 1 atmosphere. Okay, so atmospheric pressure is equal to about 14.7 psi. Okay, so that means that 14.7 psi is also roughly equal to 1 bar. Okay, and now you can kind of get a sense that if we're talking about, say, the maximum pressure or the peak pressure during a combustion process in an IC engine, right? Say a gasoline engine, well, that peak pressure is very often, somewhere around 100 bar, sometimes as high as 150 bar. But, under ordinary operating conditions, the peak pressure in an engine will be about 100 bar, right? So what that tells you is that is about 1,470 pounds per square inch, right? And so every time we drive our vehicles, our cars, those engine cylinders are holding about 1,400 psi of pressure, which is pretty remarkable if you ask me. All right, now that we basically understand the idea of gases, we know how we use volume to describe gases, we know how we use temperature to describe gases, and we know how we use pressure to describe gases. Now let's try to start to bring these properties together that we use to characterize a gas into what we call ideal gases. Okay, so let's now shift our attention to describing what is an ideal gas. And in order to understand what an ideal gas is, and this is now we're going to start to bring in portions of section 5.6 into this discussion, we need to realize that the energy in a collection of molecules of a gas are contained, or is contained, the energy is contained in three major modes. Three major modes of energy, okay? The first is what we call intermolecular energy. And this is the energy that is within a molecule itself, completely independent of other molecules in the gas and completely independent of the fact that the molecule as a whole might have a certain velocity, right? So if you, for a moment, imagine for me that this little construction that we have here is diatomic oxygen, okay? So suppose that this is O2, right? We have one oxygen atom here, and we have a second oxygen atom here, okay? Now, these two oxygen atoms are not static relative to each other, right? This oxygen atom and this oxygen, these two oxygen atoms are basically constantly vibrating back and forth relative to each other, right? So imagine you have a slinky in your hand and you've got both ends of the slinky and you're just pulling this slinky apart and pushing it back together over and over again, okay? Well, that's what atoms in a molecule do in what is called translational vibration, okay? They're translating, the two atoms are vibrating in a translational manner back and forth relative to each other, okay? Now, in addition to this vibration back and forth, this translation back and forth, this molecule can also be rotating along a certain axis, okay? And so we have basically three axes here, right? We have this axis where it can rotate this way, okay? And then we can also look in this direction at the molecule. So I'll draw it this way, where now we have this atom is here, okay? And then going into the board is the second atom, okay? And you can have essentially molecular spin, right? Where the molecule is spinning along this center axis or this center connection point between those two atoms, okay? So energy can be stored in a molecule in these three intermolecular modes, right? Translational vibration, rotational or revolutionary vibration, and then rotational vibration, okay? Okay, now the second mode of energy storage is what is called kinetic energy. And this now requires us to think of a collection of gases where suppose we have one molecule of diatomic oxygen, so O2, and then suppose we have another of diatomic oxygen, and then suppose we have a third of diatomic oxygen, okay? Well, as we discussed before, these molecules have kinetic energy, right? And so this is the velocity of one molecule, and maybe this is the velocity of the second molecule, and then perhaps this is the velocity of the third molecule, right? So because each of these molecules have velocities, it means they each have kinetic energy, right? Whenever something is in motion, it has kinetic energy, okay? And so that is a second mode of energy storage for a given gas. Now, the third is what we call intramolecular energy. Intramolecular energy is very similar to the translational mode of energy that we had with intermolecular energy. But now it's not between atoms within a molecule, but rather between molecules themselves. Okay, so suppose you have two oxygen molecules that are kind of close to each other, and what ends up happening is the positive nucleus of this molecule is attracted to the negative electron cloud of this molecule, and opposites attract. And so because this is positive and this is negative, these two molecules are going to have a tendency to come close to each other, okay? They're going to start to come closer to each other, right? They're going to attract each other. But then what happens is they start to get so close that the positive nucleus of this atom actually starts to detect the positive nucleus of this atom, and now you have similar poles, right? And they're going to repel each other. And so the two molecules then are going to push each other apart. And so you end up having that, again, that back and forth. It's very similar to that slinky concept earlier that we had with the diatomic, the atoms within the molecule, right? That translational vibration back and forth for these two atoms is basically the same concept, okay? But now it's from molecule to molecule, right? And these two molecules will repel and attract each other until they find some equilibrium point where they're essentially able to maximize how much energy they can absorb, okay? All right, so by the way, this is essentially the kinetic theory of molecules, okay? But how is this important to an ideal gas? Well, an ideal gas is one where the particles composing the gas behave independent of each other. Okay, so let's look at our three modes of energy. If we have intermolecular energy, we're talking about the energy behavior of just one particle, okay? It doesn't actually matter what the other particles are doing in the gas to influence the intermolecular energy. So, an ideal gas can have intermolecular energy as an energy mode, right? A particle can have all of these translational, vibrational, rotational, and revolutionary type modes of energy, you know, with there just being one particle in the gas, okay? So in this case, the particle can behave independent of other particles. If we look at the kinetic mode of energy, well, once again, this particle has a velocity vector of v1, which really is completely independent, or it can be completely independent of this particle, which has a velocity vector of v2, okay? So an ideal gas also has kinetic energy as a mode of energy because these two particles can behave independent of each other. Their respective velocities do not necessarily have to be influenced by the other particle. And now, of course, you can see that an ideal gas cannot have intramolecular energy, right? In other words, intramolecular energy only exists when two molecules are interacting with each other. And so the behavior of this molecule cannot possibly be independent of the behavior of this molecule in the context of intramolecular energy, how that energy is stored in an intramolecular fashion, okay? So ideal gases cannot have intramolecular energy as a mode of energy storage, okay? And that's really the key element of the kinetic theory of gases, is that ideal gases do not possess intramolecular energy mode of storage. Okay? Okay, so that's going to come up again later on when we get into the chapter that discusses thermodynamics and we talk about things like specific heat. But for now, we just need to know that ideal gases behave independent of each other. Okay, now because of this independence, and we'll later on in the next lecture actually use the kinetic theory of gases to derive this expression. We can do that from Avogadro's law, basically. Because of this particle independence, of an ideal gas, we can relate the pressure, temperature, volume, and number of moles to each other in using what is called an equation of state. Okay, so I'm not going to spend much time on this, but what an equation of state means is that, so, the equation part I'm sure that you get, but the state part refers to the fact that the substance or the control volume is in a condition where we can actually use properties, okay? We can use these various properties to describe this system, okay? To describe this control volume, okay? So when we have an equation of state, that's basically what that means, is that we can relate these properties to each other to describe everything about that state, okay? And so this is where we come up with the ideal gas equation, which is to say that the pressure times the volume is equal to the number of moles times the universal gas constant times the temperature, okay? And so we have pressure, we have volume, we have number of moles, and we have temperature. And then, of course, R is a pirate's favorite letter. Just kidding. That's actually the C. So R is the universal gas constant. Okay? Okay, now, we've spent a lot of time so far in this lecture talking about units, right? Things like atmospheres and cubic meters and Kelvin and so on and so forth. This is where units become important. This universal gas constant, this R value, it actually has several different values depending on what the units are in your ideal gas equation, okay? Your textbook is going to tell you that R, the universal gas constant, is equal to 0.08206, but this is the important part, liters, atmosphere, Kelvin, mole. Those are the units on the universal gas constant. Okay, it's kind of goofy units, but it's a constant, so it doesn't really matter. But if this is the value that you're using for the universal gas constant, what that means is the units of pressure have to be in liters, okay? The units of, I'm sorry, not pressure, the units of volume. Let me fix that. Okay, the units of volume are units, have units of liter, okay? The units on pressure would be atmospheres. The units on N, number of moles, that's of course just moles. And then the units on temperature, and this is almost always going to be the case, have to be Kelvin, okay? I say almost always only because there could sometime in your life be a chance where you use this equation in terms of Rankine or absolute English units, but then, of course, your value for R is going to be different, right? It's not going to be this 0.08206 liters atmosphere Kelvin mole, okay? Now, you could actually use a different gas constant, and this is actually the one that I'm more familiar with, where the gas constant is equal to 8.3145 joules per mole Kelvin. Okay? Now, let's talk a little bit about what a joule is, okay? A joule is a unit of energy and it's derived from the multiplication, the product of the Newton times the meter. So a joule is the same as a Newton meter, okay? All right, well, recall that the unit Pascal is equal to the Newton divided by meter squared. So that means that if I manipulate this expression, the Newton is equal to the Pascal times meter squared. And if I substitute that in for my expression for joule, then I get Pascal meter squared times meter, which is equal to Pascal cubic meter. Okay? And so I can substitute this form of the joule into this part of the universal gas constant. And so I can say that R is equal to 8.3145 Pascal cubic meter per mole Kelvin. And if I do that, well, now I could actually have the unit, going back to my ideal gas equation, I could actually have the units of Pascal, or pressure, be in Pascal, or kPa. And I could have the units of volume be in cubic meter. And I could have the units of moles, N, be in moles if I use Pascal, or kilomole if I use kilopascal. And then finally, temperature is still going to be the same, as it almost always will be, in Kelvin. Okay? Okay, a big no-no. Never, and I do mean never, use degrees Celsius for temperature in the ideal gas equation. And if you wonder why, simply assume that your gas is at 0 degrees Celsius, and now all of a sudden it also has no pressure or volume. Okay, so kind of a trivial solution. But that's why absolute temperature is so insanely important. Okay? Okay, so let's now do an example, and let's take a look at example 5.6 on page 197. And so to do that, I'm going to insert that problem here. And it's going to put it way at the top. That's the only thing I don't really care about this. Let me just move this down here. Okay, so there we go. Okay, so in this example, we have a sample of hydrogen gas, H2, and it has a volume of 8.56 liters at a temperature of 0 degrees Celsius and a pressure P of 1.5 atmospheres. And we're being asked to calculate the number of moles of H2 present in the sample. Okay? Okay, so how we can solve that? Of course, they give you the solution technique here, right? But I'll kind of walk you through it. So how they solve that is they use the ideal gas equation, PV equals nRT. And so we want to solve for N. We're given volume, that's the 8.56 liters. We're given pressure, that's the 1.5 atmospheres. And we're given temperature, that's the 0 degrees C. But caution, this is in degrees C. We're going to want to translate that to Kelvin when we actually plug this into our equation. So we can manipulate the ideal gas equation to get that N is equal to PV divided by RT. Okay? And now we can basically just do our good friend plug and chug and enter everything in. Now, one thing that is going to help you from now until the rest of your life is to always include units when doing any kind of an equation or calculation, okay? So let me write this out. N is equal to pressure, which is 1.5 atmospheres, times the volume, which was 8.56 liters, all divided by the ideal gas constant, the universal gas constant, R, which is what was given up here, 0.08206, 0.08206, and then the units on that gas constant are liters, atmospheres, divided by Kelvin mole. Okay, so this is liter, atmosphere, divided by Kelvin mole. Okay, and then that's all times temperature, which again, we want to be very careful to always have temperature in absolute. And so our temperature is given as 0 degrees Celsius. And so if we convert that to Kelvin, we just add 273.15 to that. And so this becomes 273.15 Kelvin. And so I plug that in down here, 273.15 Kelvin. Okay. Now, why did I make sure to keep track of all my units? Because now I can go through and make sure that all my units cancel accordingly. Okay, so my liters cancel, my atmospheres cancel, and my Kelvin cancels, and I'm left with moles in the denominator in this denominator, which means that moles is actually in the numerator in this expression, which of course is what I'm solving for, is the number of moles. Okay, so I plug all of this into a calculator, and I didn't do that. I'm just going to trust their calculation, and I get that N is equal to 0.57 moles. Okay, what does that mean? Well, it means to me really nothing. Okay, because I have no physical sense as to what a mole is, but it's of course important for chemistry solutions because they kind of use the mole as this arbitrary way of keeping track of particles without ever really knowing if you've got those particles or not. Okay, that specific number of particles. Okay, so let's move on now and let's take a look at our expression PV. Oh dear, what did I do here? Okay, PV equals nRT. And let's think about what happens if volume increases while moles and temperature are held constant. Okay? Well, let's take a look at our expression, right? So V is increasing, but N and T are constant, right? Moles and temperature are constant. And of course, R is also constant because it's the gas constant. It's never changing, right? And so the right-hand side of the expression is constant, but volume is increasing. Well, that necessarily means that pressure has to decrease, okay? And likewise, if volume were to decrease, then pressure would increase for the same type of constraint. Moles and temperature stay constant, okay? So what did we just describe there? This is what Boyle's law is, okay? Boyle's law is telling you the relationship between pressure and temperature when N and T are constant. Okay? All right. Let's now wonder, again using our ideal gas equation, what happens if T increases at constant N and P. Okay? Okay, so now N is constant and P is constant. So I'm going to put those two on the same side of the equation. Okay? So I have V equals N R divided by P. But then I have T over here, so I'm going to bring T over to the left-hand side. So I have V over T is equal to NRP times T. Okay? And so now I have a situation where T increases. So what does V have to do in response to that? If T increases, since the right-hand side is constant, then necessarily V also has to increase. Okay? And so this is the situation that describes Charles' law. And Charles' law is the relationship between temperature and volume when N and P are constant. Okay? Okay, there's one more. So let's just go ahead and do it. Okay? So PV equals nRT. And now we want to know what happens if N increases at constant temperature and pressure. Okay? Okay, so again, we have T and P constant. So I'm going to write this such that it's V over N. I'll put my variables on one side of the equation. And then I'll put my constant things on the other side of the equation. So this is RT over P. And so if N increases, then that means that V also increases because the right-hand side is constant. Okay? And this, of course, is the situation that describes Avogadro's law, which is the relationship between volume and number of moles when T and P are constant. Okay? So, now you know about Boyle's law, Charles' law, and Avogadro's law, and how you can derive them from the ideal gas law. Okay, last thing that I want to tell you before we do a couple of example problems is the chemistry definition for what we call standard temperature and pressure. And just as a quick FYI, this is different than the engineering definition of standard temperature and pressure, but this is a chemistry class, not an engineering class, so you have to know how chemists define it. So we refer to standard temperature and pressure as STP. And what standard temperature and pressure is it's nothing more than a reference point from which substances are described. We want all things to be described from the same reference point, and so we refer to that consistent reference point as standard temperature and pressure. So what is standard temperature and pressure? Well, the standard temperature is 0 degrees Celsius, or 273 Kelvin, and the standard pressure is 1 atmosphere. FYI, in engineering, standard temperature is 75 degrees Fahrenheit or roughly 20 degrees Celsius, okay? Because, who wants to reference everything to 0 degrees C? It's strange. Nonetheless, in chemistry, standard temperature is referenced to 0 degrees C. All right, let's go ahead and do a couple of example problems, and then that'll wrap up this lecture. So we will first do example 5.12. And again, it always puts it up at the top here. I don't necessarily know why, but this is just how it does it. So this is example 5.12. And in this case, what we have is something called quicklime, which is calcium oxide, Ca0, is produced when calcium carbonate, CaCO3, remember that Ca is calcium and carbonate is CO3, okay, is decomposed. So then what we want to know is what the volume of CO2 at standard temperature and pressure is that is produced from the decomposition of 152 grams of calcium carbonate by this reaction. And so calcium carbonate is the reactant, right? Remember that this is how we write a chemical equation. So the reactant is on the left-hand side, and then quicklime, or calcium oxide, and carbon dioxide are the products. Okay? And it's a forward reaction, meaning that the calcium oxide and the carbon dioxide cannot react with each other and go back and form calcium carbonate, okay, or at least not easily. Okay, so how do we do this? How do we actually calculate this volume, right? We want to know what so we are being asked to find the volume of CO2, okay, and we're given first of all, we're given the reaction. Okay, that's going to be important here in just a little bit. But we're also told that we have mass of calcium carbonate, CaCO3, is equal to 152 grams. Okay? Okay, so essentially what we want to do is, first of all, calculate the number of moles of calcium carbonate that is consumed, and then the number of moles of CO2 that is produced. Okay? And then once we know that the moles of CO2 can then be converted to its respective volume using the molar mass of CO2. Okay? Okay, so the molar mass of of calcium carbonate, okay, so the molar mass of CaCO3 is equal to 100.09 grams per mole. Okay, that's this value here. Okay? And so we know what our mass is. And so the mass of calcium carbonate, CaCO3, divided by the molar mass of CaCO3 is equal to the number of moles, NCaCO3. Okay? Remember that the molar mass, big M, of any substance is defined as the number of moles of that substance divided by the mass of that substance. So I'm just manipulating this equation to determine, I'm so sorry, I wrote that wrong. The molar mass is defined as the mass of a substance divided by the number of moles of that substance. Okay? So the mass of the CaCO3 is 152 grams divided by the molar mass of CaCO3, which is 100.09 grams per mole. And when we plug that into our calculator, I'll just use this value here, we get that is equal to 1.52 moles of CaCO3. Okay? Okay, now, based on the reaction, okay, the reaction is given to us right here. We know that 1 mole of CO2 is produced for every mole of calcium carbonate, CaCO3. Okay? So for this reaction, if we're consuming 1.52 moles of CaCO3, then that means that we're producing, so the number of moles of CO2 is equal to the number of moles of CaCO3. Okay, for every mole of CaCO3 we consume, we're producing 1 mole of CO2, right? There's 1 mole here, there's 1 mole here. Okay, and the equation is balanced. Okay? In other words, there's 1 calcium atom on the left-hand side, 1 calcium atom on the product side. There's 1 carbon atom on the left-hand side, 1 carbon atom on the right-hand side. There's 3 oxygen atoms on the left-hand side, and there's 1 plus 2 oxygen atoms, which is 3 oxygen atoms on the right-hand side, okay? And so 1 mole of CO2 for 1 mole of calcium carbonate, and so this is equal to 1.52 moles of CO2. And now we plug that into our molar mass. So the molar mass of CO2 is equal to, they've listed it here as 22.42 liters of, oh, I see. I'm so sorry. Okay. Okay. So because this is calculated at standard temperature and pressure, we would find that the volume is equal to 22.42 liters, okay? And so then we would say, okay, for every 1 mole of CO2 that we have, that would give us 22.42 liters of CO2. And so then we can say, since we have 1.52 moles of CO2 times 22.42 liters of CO2 per mole of CO2. We've got moles of CO2 that cancel, and then this ends up giving us 34.1 liters of CO2. Okay? And then that's the final answer. Okay, so now I had intended to do another example for you, but this thing is already over an hour long, so I'm going to stop here, and I'll pick this up tomorrow doing example 5.13. All right, hope you had fun. Bye.